Hello, my name is Charlie Colvin, and I am a rising sophomore at Penn State University, majoring in plant science. This summer, I participated in the Internet of Things for Precision Agriculture, or IoT4Ag, REU internship program at the University of Florida. IoT4Ag is an NSF engineering research center that aims to ensure food, energy, and water security by advancing technology to increase crop production while minimizing the impact of agricultural practices on the environment. Today, I'm going to share with you a little bit about my project and the work I did in Dr. Vivek Sharma's Precision Water Management Lab over the summer. Imagine you had a giant field of corn, covering hundreds of acres, and you wanted to know how much yield you could expect from that field. Now, there are certainly methods of predicting this, but most of them involve going physically into the field and taking measurements and samples of multiple plants, which is both time-consuming and expensive. Additionally, despite how they may appear, a field isn't necessarily uniform across the entire area. There can be variations in soil types, nutrient levels, soil moisture, and so on across the field, all of which can have a huge impact on the eventual yield. So, if you wanted to take samples to have an idea of what the yield might be for the whole field, you'd have to take many samples to account for this variation. Otherwise, your predictions would likely be way off. The same goes for predicting leaf nitrogen, a statistic often used by farmers to determine if a crop needs additional fertilizer. You could sample plant tissue directly, but this is a lot of effort and the samples need to be sent off to a laboratory in order to get accurate results. And, as we talked about, you'd have to take many samples at different locations to account for the in-field variations. Neither of these methods are very practical for a large-scale operation, so the goal of our research was to develop a way to accurately predict yield and leaf nitrogen from images collected from a UAV, or unmanned aerial vehicle. Essentially, we wanted to see if we could predict these statistics by just flying a drone over the field and taking pictures with an attached camera. To the human eye, a plant is green because the chlorophyll pigment in it reflects green waves and absorbs red waves. Cell structures within the plants reflect near-infrared, or NIR waves, and the amount of NIR reflected increases as the amount of photosynthesis increases. We can measure the differences in reflected wavelengths from a plant and the ratios between them in order to calculate different values, which can give us information about the health of the plants. These values that we calculate are called vegetation indexes, and using different formulas can generate different vegetation indexes. Each index is specialized to tell us certain things about the crop. Some are calibrated to be more accurate against sparse plantings, but oversaturate when the crops are dense. Others are more sensitive to disturbance from the soil, so they're only effective when the canopy is fully closed. We worked with a company to gather aerial images of our research plots over the course of the growing season. Then we used an online platform called Solvi to mark off the plots of the trial, and then to extract the reflectance data from those images. This produced a ton of raw data, which we had to go through and start to link to the different statistics like yield and leaf nitrogen, which had been calculated separately. Using simple scatter plots in Excel, we found that there was some correlation between the higher index values and higher yields, or the index values and the leaf nitrogen, but no index was a perfect predictor on its own, and there was still a substantial possibility for error. To combat this, we used machine learning to combine all the different index values and the datasets from each date to develop a unique algorithm which was far more accurate at predicting than any of the indexes alone. I would like to thank the NSF as well as IoT4Ag for providing funding for this program. I would also like to thank Dr. Sharma and all the members of the lab, the graduate students and the postdocs, for allowing me to really join them this summer and get an insight into what exactly it is they do, and teaching me as much as they can along the way. I would also like to thank University of Florida for hosting this program and for providing the housing for the summer.